Hello, welcome back. We were discussing the bivariate normal distribution, and we have found the mean of x1, mean of y, variance of x, variance of y, and the correlation coefficient, covariance, etc. Now, here we shall show a very special result, important result regarding the bivariate normal distribution. The result is that if xy, that is the vector xy has a bivariate normal distribution, then x and y are independent if and only if x and y are uncorrelated. And you have to remember that this is not a general rule for a joint distribution between any x and y. It is special to this particular distribution, bivariate normal distribution. Okay, so what we have to show is that if x and y are uncorrelated, we have to show that x and y are independent. And if x and y are independent, we can show that x and y are uncorrelated also for this particular distribution. Okay, and what is meant by x and y are uncorrelated? X and y are uncorrelated means rho is equal to 0. Okay, rho is equal to 0. And you can show this. You put rho is equal to 0. Then f of xy, that is the joint density of x and y, can be expressed as fx fy. Why? You put rho is equal to 0 in the joint density. We have discussed the joint density earlier. You can see that here this is the joint density expression. And you put rho is equal to 0 in this expression. What happens? You see, when rho is equal to 0, root of 1 minus rho square becomes 1. Okay? And when rho is equal to 0, this becomes minus 1 by 2. And the second term in the exponent vanishes because here you put rho is equal to 0. So what you get is 1 by 2 pi into sigma 1 into sigma 2 into exponent of, that is e to the power of minus 1 by 2 into x minus mu 1 by sigma 1 square plus y minus mu 2 divided by sigma 2 the whole square. That means you can write this 1 minus 2 pi into sigma 1 sigma 2 as 1 by root 2 pi into sigma 1 into 1 by root 2 pi into sigma 2. So that you can write this fxy. This f of xy can be written as fx into fy. Okay, that is very easy to verify only by putting rho is equal to 0. So what we have proved now, this means what? The joint density fxy equal to the product of the marginal densities of x and y. That means x and y are independent. So in order to show that x and y are independent, it is very easy to put rho is equal to 0 in the joint density of multivariate normal distribution. And to prove the converse, that means suppose x and y are independent. If x and y are independent, what happens? Covariance becomes 0. Okay, if x and y are independent, covariance equal to 0, and that is true for any distributions. And it is not special to the bivariate normal distribution. And if x and y are independent, covariance equal to 0, and therefore correlation is also equal to 0. Okay, so the converse part is true for any joint distribution for x and y. But the first part is not so. It is specifically for the bivariate normal distribution. So this is actually a characterization of bivariate normal distribution. For bivariate normal distribution, uh, if x and y are uncorrelated, then x and y are independent. And if x and y are independent, x and y are uncorrelated. Okay. And then we come to the uh, uh, derivations of marginal distributions of x and that of y. And similarly, what are the conditional distributions of x given y and for y given x? And you can see the for the proof we write, suppose x and y are bivariate normal with this density, okay, this is the density. And how would you find the marginal distribution of x? You can write the marginal density of x by integrating fxy with respect to y. That is, you integrate the joint density with respect to y, you will get the marginal density of x. And similarly, in order to get the marginal density of y, you have to integrate the joint density with respect to the other variable, that is x. Okay, now first we find the marginal density of x. So the formula fx equal to minus infinity to infinity fxy dy. And for making this integration, you can put v is equal to y minus mu 2 by sigma 2. This is the first substitution we have to make for integration. And as in the earlier case, you complete the square on y, we can see that the marginal density of x is fx equal to minus infinity to infinity 1 by 2 pi into sigma 1 root of 1 minus rho square. And you can see that this is equal to e to the power of minus 1 by 2 into x minus mu 1 by sigma 1 square minus 1 by 2 into 1 minus rho square into v minus rho into x minus mu 1 by sigma 1 whole square dv. And you can see that here you are having 2 pi into sigma 1 only. Sigma 2 disappears. Why sigma square disappears? You can take this, this is equal to sigma 2 into dv, that is equal to dy. Using that, you can cancel that sigma 2 in the denominator with a sigma 2 into dv. And on simplification, you will get this expression. And again, you make a substitution for integration. So two stages of substitutions are required for completing this integration. Now you substitute, you put this omega, that is equal to v minus rho into x minus mu 1 by sigma 1 divided by root of 1 minus rho square. Therefore, you can put this quantity with this 1 minus rho square in the denominator as omega square. Okay, and you can easily see that d omega, that is equal to dv by root of 1 minus rho square. So this 1 minus rho square and this 1 minus rho square will be getting you can see this quantity will be getting cancelled with this. This quantity will go to the numerator first, and you can see that 1 minus rho square square root will be cancelled with this root of 1 minus rho square when it becomes in the numerator. Okay, and we can easily show that by some simplification. You can see that this f of x equal to 1 by root 2 pi into sigma 1 square e to the power of minus 1 by 2 into x minus mu 1 divided by sigma 1 square. ഇത് കഴിഞ്ഞിട്ട് ഒരു ഇൻ്റഗ്രൽ കൂടി ഉണ്ടാവും, ഇൻ്റഗ്രൽ, but that integral is with respect to a standard normal distribution, so that integral is equal to 1. And on making use of that, you will finally see that this f of x equal to 1 by root 2 pi into sigma 1 square. Okay, some intermediate steps I have skipped here, but you can easily complete those steps. Okay, and you see what is the density. By seeing this form, this density is nothing but the density of a normal distribution with mean mu1 and variance sigma 1 square, or standard deviation sigma. Okay, so you see that the distribution of x, that is actually the marginal distribution of x, is again a normal distribution whose parameters are mu1 and sigma 1. Okay, and the same technique you can apply for finding the marginal density of y, that is fy of y. You can find fy of y will be equal to 1 by root 2 pi into sigma 2 square into e to the power of minus 1 by 2 into y minus mu 2 divided by sigma 2 the whole square. Okay, now these are the things for the marginal densities of x and y in a bivariate normal distribution. That is also a very important and interesting result for this particular distribution. And again, now we can find what are the conditional distributions. And here also you can see that, later you will see that the conditional distributions are also normal distributions. Okay, conditional distribution x given y and conditional distribution of y given x, both are normally distributed. Both are normal distributions. But the parameters will have a little variation, and you will see what are the variations. Because before this coming to the proof of this result, you again catch the point. One, for bivariate normal distribution, marginal densities are normal and conditional distributions are also normal. Now for finding the conditional density, you can use the usual formula for this conditional distribution or conditional density. What is the conditional density of x given y? You can denote this by fx given y of x given y. Now this x given y stands for the random variables, and this for the values. And by the formula, a very familiar formula for you, that it is the ratio of the joint density to the marginal density of the given variable. That is fx given y is equal to fxy by f of y. And similarly, the marginal density of y given x, what will be this? It is also equal to the ratio of joint density in the numerator, and denominator the marginal density of x. Okay, now we try to find what is fx given y. Okay, now you can see that by taking the joint density in the numerator and the marginal density in the denominator, you can simplify this ratio into 1 by root 2 pi into sigma 1 root of 1 minus rho square into e to the power of minus 1 by 2 sigma 1 square 1 minus rho square into x minus mu 1 minus rho into sigma 1 by sigma 2 into y minus mu 2 the whole square. And this requires some simplifications, and I have skipped the steps behind this result, and you can easily complete these steps. Okay, and the final result is this 1 by root 2 pi into sigma 1 root of 1 minus rho square, etc. And by seeing this form of density, you can identify what are the mean and standard deviation of that distribution, or equivalently the density. You can see that the standard deviation is sigma 1 into root of 1 minus rho square, and mean is equal to here this is x minus mu1 minus etc. So this is, you can write x minus of mu1 plus rho into sigma 1 by sigma 2 into y minus mu2. Okay, so by identifying the mean and variance of the standard mean and standard deviation of this density, you can see that mean is mu1 plus rho into sigma 1 by sigma 2 into y minus mu2, and variance is 1 minus rho square into sigma 1 square. Okay, what is the form of the density of normal distribution? It is a f of, for example, suppose x follow normal with mean mu and variance sigma square. So the density will have 1 divided by root 2 pi into the standard deviation into x e to the power of minus 1 by 2 into x minus mean divided by the standard deviation whole square. So by identifying with this form of density, you can easily deduce the mean and variance as mu1 plus rho into sigma 1 by sigma 2 into y minus mu2, and variance 1 minus rho square into sigma 1 square. Okay, and the same technique you can apply for finding the marginal density of y given x. The only thing is that you have to interchange x and y, so that the final result will be very obvious, and you will see that the conditional density or conditional distribution of y given x is also normal, with the mean mu2 plus rho into sigma 2 by sigma 1 into x minus mu1, and variance equal to 1 minus rho square into sigma 2 square. Okay, now you see here in these final results, you see the mean is in terms of given y. Okay, because here you are finding the marginal distribution of x when y is given, so naturally that mean may be in terms of the given value of y. And similarly here you are finding the marginal density of y given x. Since x is given, naturally you can expect the mean in terms of that given x. Okay, so it is not a surprise, it is quite obvious. So we stop this section by adding these two results regarding the marginal distributions of x and y, and the conditional distributions of x given y and y given x. Okay, thank you.